Solar energy in the atmosphere. Earth's atmosphere is heated by the transfer of energy from the sun. Some of the heat in the atmosphere comes from the absorption of the sun rays by gases in the atmosphere. Some heat enters the atmosphere indirectly as ocean and land surfaces absorb solar energy and then give off that energy as heat. Radiation. All of the energy that Earth receives from the sun travels through space between Earth and the sun as radiation. Radiation includes all form of energy that travels through space as waves. Visible light is the form of radiations that human eyes can detect. However, there are many other forms of radiations that humans cannot see, such as ultraviolet light, X-rays, and radio waves. Radiation travels through space in the form of waves at the very high speed, approximately 300,000 kilometers per second. The distance from any point on the wave to the identical point on the next wave, for example from crest to crest, is called the wavelength of the wave. The various types of radiation differ in length of their waves. Visible light, for example, consists of waves that have various wavelengths that are seen as different colors. The wavelengths of those ultraviolet rays, X-rays, and gamma rays are shorter than those of visible light. Infrared waves and radio waves have a relatively long wavelength. The wavelengths that make up all forms of radiation is called electromagnetic waves. Almost all of the energy that reaches the Earth from the sun is in the form of electromagnetic waves. The electromagnetic spectrum, shown on the bottom of Figure 1, consists of the complete range of electromagnetic waves, from radio waves to gamma rays, with radio being longest, 10 times 10 to the fourth, all the way down to 10 times 10 to the negative 14th. The atmosphere and solar radiation. As solar radiation passes through Earth's atmosphere, the atmosphere affects the radiation in several ways. The upper atmosphere absorbs almost all radiation that has a wavelength shorter than the wavelengths of visible light. The molecules of nitrogen and oxygen in the thermosphere and the mesosphere absorb the X-rays, gamma rays, and ultraviolet rays. In the stratosphere, ultraviolet rays are absorbed and act upon oxygen molecules to form ozone. Most of the solar rays that reach the lower atmosphere, such as visible and infrared waves, have longer wavelengths. Most of the incoming infrared radiation is absorbed by carbon dioxide, water vapor, and other complex molecules in the troposphere. As visible light waves pass through the atmosphere, only a small amount of this radiation is absorbed. Figure 2 shows the percentage of solar energy that is reflected and absorbed by the atmosphere. Scattering. Clouds, dust, water droplets, and gas molecules in the atmosphere disrupt the path of the radiation from the sun and cause scattering. Scattering occurs when the particles of the gas molecules in the atmosphere reflect and bend the solar rays. This deflection causes the rays to travel out in all directions without changing their wavelengths. Scattering sends some of the radiation back into space. The remaining radiation continues towards the Earth's surface. As a result of scattering, sunlight that reaches the Earth's surface comes from all directions. In addition, scattering makes the sky appear blue and makes the sun appear red at sunrise and sunset. The ozone hole. Ozone, O3, is a naturally occurring gas that is present primarily in the stratosphere. The thin layer of ozone that surrounds the Earth prevents the sun's ultraviolet radiation from reaching the Earth's surface. Overexposure to UV radiation is dangerous to living things because it damages DNA. DNA is the genetic material that carries the information from inherited characteristics. UV radiation also makes the body more susceptible to skin cancer. The protective ozone layer is not distributed around the Earth evenly. Scientists have observed ozone concentrations vary with latitude and with the time of the year. In 1985, scientists discovered that the ozone layer was unusually thin in regions over Antarctica. This ozone hole allows greater amount of UV radiation to reach the Earth's surface. Scientists discovered that chemicals called chlorofluorocarbons, CFCs, were causing the ozone layer to break down. CFCs were used as coolant and refrigerant in air conditioners. CFCs were also used in spray cans such as those for household products and paint. The discovery of a connection between CFCs and the weakening ozone layer led to the international ban on CFCs. CFCs can act to destroy ozone continuously for 60 to 120 years. So CFCs released 30 years ago may still be destroying ozone today. It will take many years for the ozone layer to completely recover. Reflection. When solar energy reaches the Earth's surface, the surface either absorbs or reflects energy. The amount of energy that is absorbed or reflected depends on characteristics such as color, texture, composition, volume, mass, transparency, states of matter, and specific heat of the material on which the solar radiation falls. The intensity and amount of time that the surface material receives radiation also affects how much energy is reflected or absorbed. The fraction of solar radiation that is reflected by a particular surface is called the albedo. Because 30% of the solar energy reaches the Earth's atmosphere is either reflected or scattered, Earth is said to have an albedo of 0.3. Table 1 shows the amount of incoming solar radiation that is absorbed or reflected off various surfaces. Absorption and infrared energy. The sun constantly emits radiation. Solar radiation that is not reflected is absorbed by rocks, solar, water, and other surfaces. When the Earth's surface absorbs solar radiation, the radiation's short wavelength infrared rays and visible light heat the surface materials. When the heated materials is converted to energy into infrared rays of long wavelengths and re-emit those wavelengths, gas molecules such as water vapor and carbon dioxide in the atmosphere absorb these infrared rays. The absorption of thermal energy from the ground heats the lower atmosphere and keeps the Earth's surface much warmer than it would be if there was no atmosphere. Sometimes warm air near the Earth's surface bends light rays to produce an effect called a mirage, as shown in Figure 3. Solar radiation passes through the atmosphere and warms the Earth's surface. Energy from the sun is absorbed by the Earth's surface and then radiated into the atmosphere as heat, some of which escapes into space. Greenhouse gases also absorb some energy from the Earth and radiates it back towards the lower atmosphere and the Earth's surface. The greenhouse effect. One of the ways in which the gases of the atmosphere absorb and re-radiate infrared rays, shown in Figure 4, can be compared to the process that keeps a greenhouse warm. The glass of a greenhouse allows visible light and infrared rays from the sun to pass through the warm the surface inside the greenhouse, but the glass prevents the infrared rays that are emitted by the warmed surface within the greenhouse from escaping. Similarly, the Earth's atmosphere slows the escape of energy that radiates from the Earth's surface. Because this process is similar to the process that heats a greenhouse, it is called the greenhouse effect. Human impact on the greenhouse effect. Generally, the amount of solar energy that enters the Earth's atmosphere is about equal to the amount that escapes into space. However, human activity may change this balance and may cause the average temperature of the atmosphere to increase. For example, measurements that indicate that the amount of carbon dioxide in the atmosphere has been increasing in recent years. These increases have been attributed to the burning of more fossil fuels. These increases seem likely to continue in the future. The increase in the amount of carbon dioxide may intensify the greenhouse effect and may cause Earth to become warmer in some areas and cooler in others. Variation in temperatures. Radiation from the sun does not heat the Earth equally at all places at all times. In addition, a slight delay occurs between the absorption of energy and the increase in the temperature. Earth's surface must absorb energy from a time before enough heat has been absorbed and re-radiated from the ground to change the temperature of the atmosphere. For a similar reason, the warmest hours of the day are usually mid to late afternoon, even though solar radiation is most intense at noon. The temperature of the atmosphere in any region of the Earth's surface depends on several factors, including latitude, surface features, and the time of the year and day. Latitude and season. Latitude is primary factor that affects the amount of solar energy that reaches any point on the Earth's surface. Because the Earth is a sphere, the sun rays do not strike all areas at the same angle, as shown in Figure 5. The rays of the sun strike the ground near the equator at an angle near 90 degrees. At the poles, the sunlight strikes the ground at a much smaller angle. When the sunlight hits the Earth's surface at an angle smaller than 90, the energy is spread out over a larger area and is less intense. Thus, the energy that reaches the equator is more intense than the energy that strikes the poles. So average temperatures are higher near the equator than are near the poles. Temperature varies seasonally because of the tilt of the Earth's axis. As the Earth revolves around the sun each year, the portion of the Earth's surface that receives the most intense sunlight changes. For part of the year, the northern hemisphere is tilted towards the sun and receives more direct sunlight. During this time of the year, the temperatures at their highest. For the other part of the year, the southern hemisphere is tilted towards the sun. During this time, the northern hemisphere receives less direct sunlight, and the temperature there is at the lowest. Water in the air and on the surface. Because water vapor stores heat, the amount of water in the air affects the temperature of a region. The thinner air at the high elevation contains less water vapor and carbon dioxide to absorb the heat. As a result, those areas become warm during the day but cool very quickly at night. Similarly, desert temperatures may vary widely between day and night because little water vapor is present to hold the heat of the day. Land areas so close to large bodies of water generally have more moderate temperatures. In other words, those areas will be cooler during the day and warmer at night than inland regions that have the same general weather conditions. The reason for these moderate temperatures is that water heats up and cools down faster than air does. The reason for these moderate temperatures is water heats up and cools down faster than the air does. So the temperature of the water changes less than the temperature of the land does. The wind patterns in the areas also affect the temperature. A region that received winds off the ocean water has more moderate temperature than does similar regions in which the winds blow from the land. Conduction. The molecules in a substance move faster as they become heated. These fast-moving molecules cause other molecules to move faster. Collision between the particles result in the transfer of energy, which warms the substance. The transfer of energy as heat from one substance to another by direct contact is called conduction. Solid substances in which the molecules are close together make relative good conductors because the molecules of the air are far apart, as air is a poor conductor. Thus, conduction heats only the lowest few centimeters in the atmosphere where the air comes into contact with the warmed surface of the air. Convection. The heating of the lower atmosphere is primarily the result of the distribution of heat through the troposphere by convection. Convection is a process by which air and other matter rises or sinks because of the difference in temperature. Convection occurs when gases or liquids are heated unevenly. As air is heated by radiation or conduction, it becomes less dense and is pushed up by nearby cooler air. In turn, the cooler air becomes warmer and the cycle repeats. The continuous cycle in which cold air sinks and warm air rises warms the Earth's atmosphere evenly. Because warm air is less dense than cool air, the warm air exerts less pressure than the same volume of cooler air. So the atmospheric pressure is lower beneath the mass of warm air. As dense air moves into low pressure regions, the less dense, warmer air pushes upwards. This pressure difference, which are the result of unequal heating, causes convection, creates wind.